Hello everyone, welcome to Chem Analysis. In today's video, I will solve previous year CSIR-NET questions that were asked in June 2019, and here I will mainly solve 2-marker inorganic chemistry questions. So without further delay, let's start the question answer series. As you can see that the first question is asked from analytical chemistry, and you have to answer or you have to say the role of H3PO4, that is phosphoric acid, in the estimation of iron 2 with potassium dichromate titration using diphenylamine sulfonate as the indicator. Now to solve the question, first of all, since you can see that it is a redox titration, so we have to know the redox potential for a different half cell. So first of all, potassium dichromate, here chromium is in +6 oxidation state and it will go to chromium 3, and if you see the redox potential for this, it will be 1.33 volt. And similarly for iron 3 to iron 2, the redox potential will be it is 0.77 volt. And there is another redox active species, that is diphenylamine sulfonate, and the redox potential for this system is between 0.7 to 0.8 volt. Now since the redox potential of the indicator is near the range of the redox potential of iron 3 iron 2 system, so there is a possibility that the oxidizing agent potassium dichromate will oxidize diphenylamine sulfonate as well as iron 2 to iron 3. Therefore, to overcome this difficulty, we have to do something so that we can reduce the redox potential of this iron 3 iron 2 system, and for this phosphoric acid is used. Since in presence of phosphoric acid, it will complex with the iron 3 species, H3PO4 will form a complex with iron 3, and therefore we reduce the concentration of iron 3, and the redox potential of iron 3 iron 2 system will reduce. Since the half cell redox potential will be like this, log concentration of Fe2 plus, that is Fe2, and concentration of Fe3. Since the concentration of Fe3 in the reaction medium is decreasing due to presence of phosphoric acid, the redox potential for this Fe3 Fe2 system will decrease and it will reach near about 0.61 volt. Now the problem is gone. Since the redox potential of this indicator is higher than that of this iron 3 iron 2 system, the oxidizing species potassium dichromate will mainly oxidize iron 2 to iron 3, leaving the indicator as intact, and therefore we can calculate the amount of iron 2 in the complex. Thus we can see or we can say that phosphoric acid is used to reduce the redox potential of iron 3 to iron 2. So option number 2 is the correct answer. In the second question, we can see that this is asked from bioinorganic chemistry, and we have to tell about the correct answer for this superoxide anion. The first option is it is asked the superoxide anion having a shorter O bond length than that of oxygen, and for that you have to know the molecular orbital diagram of oxygen. If you draw the molecular orbital diagram of oxygen, you will see that there is 2 unpaired electron in the pi star orbital of oxygen, and when O2 is converting to O2 radical minus, that is superoxide anion, 1 electron is coming to the pi star orbital, and since the incoming electron is coming to the antibonding orbital, bond order of superoxide anion will be less than that of oxygen, and since bond order is decreasing, bond length of OO in superoxide anion will be higher than that of oxygen. So the first option is not correct. And superoxide anion, you know that superoxide or peroxide are more stronger oxidizing agent than that of oxygen. So you can see that second option is correct. And for IR activity, since superoxide anion is homodiatomic molecule, so it will be IR inactive. and since there is a anionic charge, it can easily abstract proton from a weak acid also. And on the other hand, it is also a stronger oxidizing agent, so it can easily abstract proton from a weak acid. So this option is also not correct. It is able to abstract proton from weak acid. So the correct answer is option number 2. In the third question, the question is asked from neutron activation analysis. And what is neutron activation analysis? The short form is NAA. In this procedure, this technique is applied for the detection of concentration of element in a complex, and in this study the complex is activated by neutron, and during activation the rays which is radiated is the gamma rays. So is it okay? So next, go to the next question, and you have to tell the metal which is transferred by the bacterial fungi using siderophores or siderochromes. Siderophores or siderochrome are iron containing chelating complex. So the metal which is transferred by siderophores or siderochromes is iron. This is a very important question and you have to think properly. It is asked that the self exchange electron transfer is fastest in which of this complex. Now first of all, you have to first identify that the complex will show inner sphere electron transfer or outer sphere electron transfer. Since the ligand attached to the metal center are not coordinating ligands, so it will mainly exhibit outer sphere electron transfer. And among the few conditions, one of the important condition for the outer sphere electron transfer to happen is that the metal complex that are involved should be inert. And if the electron transfer occurs from T2G to T2G, then the electron transfer will be faster in comparison to EG to EG electron transfer or EG to T2G electron transfer. Okay. And the complex should be inert instead of labile. Now if you consider the metal complex, in the first case you will see that there is ruthenium 2 and ruthenium 3, and ruthenium is a metal for 4D series, and the ligand attached to the ruthenium center is ammonia, that is a strong field ligand. So ruthenium 2 will be low spin complex and it will be T2G6 and EG0. Similarly ruthenium 3, it will be T2G5, that is ruthenium in both the oxidation state is in low spin complex, that is inert. Okay. For cobalt case, cobalt 2, since ammonia is a strong field ligand, the complex will be low spin, and since cobalt is D7 complex, cobalt 2 is D7, so it will be T2G6 EG1, and cobalt 3, it will be T2G6 and EG0. So these two oxidation state also, these two complex also inert. And on the other case, chromium, since H2O is a weak field ligand, both the two complex of chromium and iron will be in high spin oxidation state. So chromium 2, since it is D4, so T2G3 EG1, and it will be labile, and chromium 3, that is T2G3, it will be inert. On the other way, iron 2, since it is D6 system, T2G4 EG2, it will be labile, and iron 3, that is T2G3 EG2, it is also labile. So these two complex will not show outer sphere electron transfer complex, or maybe so, but that electron transfer will be slower. Now since ruthenium and cobalt complex are inert, they will show higher rate of electron transfer. Now between ruthenium and cobalt, you can see that in case of ruthenium, the electron transfer from ruthenium-2 to ruthenium-3 will occur from T2G to T2G. But in case of cobalt, the electron transfer will occur from Eg to Eg. Since I have told previously that T2G to T2G electron transfer is more faster than Eg-Eg or Eg to T2G. So in case of ruthenium complex, the electron transfer will be fastest. Is it okay? If you have any question, you can ask me in the comment section. It is a very easy question. We have to calculate the number of nickel-nickel bonds in this complex that will follow 18 electron rule. And to calculate that, you have to count the number of electron around the central metal center. That is, here is Cp nickel mu PpH2. PpH2 will act as a bridging ligand and it will be 3 electron donor, since phosphorus will contain 5 electron and 2 electron is involved in the bonding with phenyl ring, and there will be 3 electron. So each PpH2 ligand will contribute 3 electron to the metal center. So if you count the total number of electrons in this complex, so it will be, there will be 2 multiplications since it is a dimer. So for Cp, if we consider it as a neutral ligand, so it will contribute 5 electron. For nickel, it will be in 0 oxidation state, so it will contribute 10 electron. And PpH2 ligand will contribute 3 electron, so the total electron will be 13 plus 5, 18, that is 36 electron. And the number of nickel-nickel bond will be 18N minus total valence electron, that is 36. It is the total valence electron. And here N is equal to 2, since it is a dimer, so there will be 2 metal center, minus 36. Therefore the number of nickel-nickel bonds will be 0. There will be no nickel-nickel bonds. And if you draw the structure, it will look like, here will be Cp ligand, here will be Cp ligand, and the PpH2 ligand will form a bridge like this. If it donate 1 electron to this nickel center, it will donate 2 electron to this nickel center. And similarly, this in that case, this phosphorus atom will donate 1 electron to this nickel center and 2 electron to this nickel center. Okay. And it is just a simple chemical reaction. You have to tell about the reaction between iodide and iodate in acidic medium, aqueous acidic medium, that is, there will be H plus. Since there is 3 oxygen and the proton will end up in generating H2O, so here will be 6H plus, and if we balance the charge, then it will be 5I minus, and in the right hand side there will be 3I2 and H2O. So in the reaction between iodate and iodide in aqueous acidic medium, it will result iodine and water. And this is also a very simple question. It is from Isolable chemistry. We have to count the number of electron around the metal center. Here iron is in 0 oxidation state, since carbon monoxide and PpH3 both are neutral ligand. So iron will contribute 8 electron, 2 carbonyl will contribute total 4 electron, and 1 PpH3, that means 2 electron, and since there is 1 negative charge, it will contribute 1 electron, that is 8, 4, 12, 14, 15. There is 15 electron, and it is 3 electron less than that of 18 electron. So among this given organic species, the species which will be 3 electron less than that of nearest octet, that will be isolable to this organometallic complex. Now if you count the number of electrons for this organic species, here printing is not very good, it is CH2. So for CH2 the number of electron will be 4 plus 2, that is 6, and it is 2 electron less than that of octet. For CH minus there will be 4 plus 1 plus 1, it is for negative charge, it is also 6 and 2 electron less, so it is also not isolable to the given organometallic complex. For CH3, 4 plus 3, that is 7, and it is 1 electron less than that of nearest octet, so it is also not isolable. And for the last CH, that is 4 for carbon and 1 for hydrogen, that is 5, and it is 3 electron less than that of nearest octet, so it will be isolable. CH will be isolable to this given organometallic complex, so 4 will be correct answer. In the next question, you have to tell about the oxidation state of sulfur in dithionous acid. You have to just know the structure of these two acid, that is dithionous acid, and the structure of dithionous acid is like this. And here you can easily count the oxidation state of sulfur atom, since both the sulfur atom are equivalent, and the oxidation state for both the sulfur atom will be 3. And for dithionic acid, the structure is like this. There will be one more oxygen atom, so the oxidation state for both the sulfur atoms, since both are equivalent, oxidation state is +5. So in dithionic acid it is +3, and dithionic acid it is +5. Option number 3 is the correct answer. It is a conceptual based question. We have to tell about the stability constant of HgX formed by the reaction between Hg2 plus and X minus. X minus are the halide. This question can be solved depending upon the HSAB principle, that is Hartrop acid base principle. Here it will be act as a acid and anion will act as a base, and you know that hard interaction and soft interaction are stronger than that of hard soft interaction. Okay, and here Hg2 plus, since it exists or it presents in the periodic table at below, and the oxygen state is also not high, so it will act as a soft metal center, that is soft acid. And now depending upon the hardness or softness of the halide ligand, the stability of the complex will be determined. With increasing the softness of the halide, the stability of the complex will increase. Now among the halogen, the softness, nature of softness, that is order of softness, will be like this, that is fluoride will be harder than that of chloride, and bromide will be softer in the given 3 halide. So the stability of HgX complex will be stronger, that is the stability will be highest for bromide minus, for bromide, then chloride, and then fluoride. It will purely governed by the hard soft interaction. So you can see that option number A will be the correct answer. Is it okay? Now this is a question from coordination chemistry, and you have to tell about the coordination number of gadolinium in this complex. You cannot write this complex like this, that is you can simply say that gadolinium, this complex will present as this, and Cl3 will be outside the bracket. And if you think that the structure is like this, the coordination number of gadolinium will be 6, but it will not be correct. The exact configuration of this complex will be like this: 6 water, and there will be 2 chlorine ligand inside the coordination sphere, and therefore the exact coordination number for this complex will be 8, not 6. Okay. And in the next question, we can see that we have to tell about the correct statement about the pi molecular orbital of benzene. Now for that you have to draw the pi molecular orbital of benzene, and you have to tell about the statement regarding HOMO and LUMO. That is the degeneracy of HOMO and LUMO you have to tell. Now if you see since in benzene there is 6 p orbital involved in forming the molecular orbital, there will be 6 pi molecular orbital. And to find out simply the molecular orbital of benzene, you can watch my previous video on Huckel molecular orbital theory. I have discussed that how to calculate the different molecular orbital for a cyclic or as well as acyclic conjugated system. And for benzene, if you calculate the pi molecular orbital, you will be see that psi 1 will be the energy for psi 1 will be alpha plus 2 beta, and psi 2 and psi 3, that is they will be degenerate, and the energy will be alpha plus beta and alpha plus beta. Next, the next two pi orbital will be also degenerate, that is alpha minus beta, energy is alpha minus beta and alpha minus beta, and the last orbital, that is psi 6, the energy for that will be alpha minus 2 beta. And if you put the 6 electron in the pi molecular orbital, then the HOMO will be psi 2 and psi 3, that is they are degenerate. So HOMO is doubly degenerate, we can see here. And the LUMO, the lowest unoccupied molecular orbital, will be psi 4 and psi 5, and they are also degenerate, that is LUMO is also degenerate. For benzene, both HOMO and LUMO are doubly degenerate. Okay, so among the given 4 options, we can see that option number 4 is the correct answer. You can watch my previous video on Huckel molecular orbital theory. You can easily solve that, or you can easily identify the energy of the different pi molecular orbital of benzene as well as different acyclic system. So now this is the last question for this discussion, and here we have to tell about the order for the reaction of this trans iridium X CO PPH3 whole 2 with O2. And since O2 is an oxidizing agent, and the reaction between these two complex, this complex and O2 will be oxidative addition. And the preliminary condition for the oxidative addition to occur efficiently is that the central metal center will be in lower oxidation state and will be electron rich. And if these two conditions satisfied, the complex will undergo faster oxidative addition. Now here the oxidation state of iridium is +1, that is it is in lower oxidation state, and now the electron density on the iridium center will depend on this halide ligand, that is X, since other 3 ligand will be same in all the cases. This will be PPH3. Now among the halogen, the electronegativity order is like this, and depending on this electronegativity, the electron density on the iridium center, since more electronegative fluorine atom will attract more electron density towards it, and it will make the iridium center electron deficient. So electron density order for this different iridium complex will be, for iridium fluorine it will be least, then iridium chloride, it is purely governed by the electronegativity of the halogen. Thus, as I said here, higher the electron reach the metal center, higher will be the rate of oxidative addition. So the rate of reaction for this 4 complex, that is for this 4 halide, will be this one, that is for iodine the rate will be highest, then bromine, then chlorine, then fluorine. It is mainly dependent on the electron density on the iridium center. So you can see that option number 4 is the correct answer. So that's all for this discussion. If you like it, you can also share it with your friends, and please like this video, and if you are new in this channel, then don't forget to subscribe my channel Chem Analysis. Thank you once again.